Let's go ahead and use these ideas to calculate the pH of an acid. And if we have an acid, it's a lot easier to work with a strong acid. And we'll work with a weak acid here in a little bit, but it takes a little bit more effort. So we've got a strong acid, so for example, like nitric acid. So nitric acid is HNO3, and it is strong. And if you remember what strong means is that it completely breaks down and dissolves and forms ions in solution 100% of the time. So it's a monoprotic acid, so there's one H plus for every nitric acid, and when it breaks down it makes H plus and NO3 minus. And maybe we've got a concentration of nitric acid that is, say, 0.13 molar, and we want to know the pH of this acid. So the way we're going to do that is we're going to use the fact that it completely breaks down. And so that means that if there is 0.13 moles of HNO3 in a liter, there will be exactly that same number of moles in a liter of H plus and of NO3 minus. So the concentration then of H plus is 0.13 molar. The concentration of nitrate is 0.13 molar. The osmolarity of that solution is 0.26 molar, where we add them up just for fun. But of course, the osmolarity's got nothing to do with pH. That was just kind of a fun throwback, I suppose. And this is really the thing we need to keep our eye upon. So the pH is the negative log of the H plus concentration. So, so pH is negative log of H plus. That is then the negative log of 0.13 molar. We don't ever put the units in there. We can't take the log of something with units. And if we calculate that, the log of 0.13 is negative 0.89. And of course, the negative means that we switch the sign. So it's positive 0.89. And again, the number of significant figures becomes the number of decimal places. So the pH is 0.89. That's quite acidic. Now we can try our luck with calculating the pH of a weak acid, and the problem with a weak acid is that it undergoes less than 100% dissociation. So we're going to have to know what percent of the acid actually breaks down. And an example of a weak acid might be acetic acid. So maybe we've got some acetic acid. One way to write acetic acid is HC2H3O2. And that is the acid that is in vinegar. And we're going to say that this is going to undergo dissociation at a 3% rate. So only 3 out of 100 molecules will break down. And the acidic hydrogen is the one up front or the one at the end. And the hydrogens in the middle are normally not considered to be acidic by convention. So we can go ahead and we can write the H plus ion, and C2H3O2 minus, that's the acetate ion, the counter ion here. And what we're doing, right, is we're saying it's 3%. So what would be a good concentration? Well, how about if we had some 0.1 molar acetic acid and we want to know its pH? So we would undergo this as follows. So we would say it's 0.1 molar, and 3% of it is breaking down. So it's 1 to 1 here. So we're going to have 3%. That's 3 over 100 times by 0.1 molar of H plus. And we'd have the same thing for the acetate concentration, but we don't need to know this to find the pH. What's 3% of 0.01? I believe that is 0.0030 molar. So that's the concentration of H plus. And the pH is just the negative log of that concentration. So pH is minus log H plus. So that is minus log 0.0030. Again, the convention is to leave the units off. And if we go ahead and we calculate that pH, we get 2.52. Again, remember the number of significant figures here, which is 2, becomes the number of decimal places here. So the pH is 2.52. We might compare that to maybe some 0.1 molar hydrochloric acid. So what about some stomach acid? So what about some 0.1 molar hydrochloric acid? Hydrochloric acid is strong. And if it is strong, then we know it completely breaks down. So the HCl completely breaks down into H plus and Cl minus. Okay, the H plus concentration, well, if HCl is 0.1 molar and we're undergoing 100% dissociation, then the H plus concentration is 0.1 molar. And if we go ahead and just move that up off the screen a little bit, there we go. And now we can calculate the pH. The pH is the negative log of the H plus concentration. For a strong acid, then that if it's monoprotic, it's essentially the same as the acid concentration itself. So that is log 0.1. and that comes out to be 1.00, where remember the number of significant figures becomes the number of decimal places. And if we look at how that compares, right, so the acetic acid was 2.52 and the hydrochloric acid was 1. So if we look at the acidity here, so remember here's the pH scale, and here's 7 where it's neutral, and above 7, right, it is basic, and below 7 it was acidic. So what did we have? We had our 2.52, which was pretty acidic because it's much lower than 7. But if we compare that to the hydrochloric acid was at 1. So although both those acids were at exactly the same concentration, and in our problem we took them both to be 0.1 molar, so you might say, well, if they're the same concentration of acid, surely they'll be just as acidic, surely they'll have the same pH. But it turns out because the HCl broke down completely, the pH is much lower because it's making more H plus ions when it completely breaks down. And the acetic acid, only 3 out of 100 were breaking down, so you only got 3 out of 100 as many H plus ions, and so the pH is 2.52. And again, this is a logarithmic scale, so you might say, well, that's not too far apart really, but this is 1.5 units apart, so that's quite significant. For every unit, it's a factor of 10, so that's quite a difference there in the H plus concentration in the solution.